In this video, we're going to cover a concept called f-stop. In brief, f-stop is simply one of the settings on your camera that uses a set of numbers to determine how much light is coming into the camera through the lens. If we look at a top-down view of our camera here, we have a lens up here at the front, we have our film or sensor at the back, and in between these two is a mechanism called the iris. The iris is basically a circular shield with a hole in the center that can open or close depending on how much light you want to let in the camera. The hole itself is called the aperture. The mechanism that's making this hole is called the iris. This is good to know because most of the time you'll see the aperture referred to, but sometimes you'll see the iris referred to. And it's just good to know that we're just interested in the aperture. So the effect of this is that with an aperture open wide, you're going to be letting in a lot of light into your camera through the lens. But with a small aperture, you're not really going to be letting in that much light. The f-stop numbers are basically a scale of numbers for talking about how much light we want coming into the camera with regard to how wide open the aperture needs to be to get that amount of light. With the f-stop scale of numbers, every major point on the scale either doubles or halves the amount of light, depending if you're going up or down the scale. So if we have these different aperture sizes here, every time we go to the next aperture size, we're doubling the amount of light. But we need to pay attention to one interesting thing here about the size of the aperture. Let's use this one for example and say it's got a diameter of 20 millimeters. That means the area of the aperture is 314 millimeters. This is important because basically the area of the aperture is saying this is how much light we're letting through this aperture. So if we go up to the next size aperture in the f-stop scale, we're doubling the area of the aperture, which means we're saying we're letting in double the amount of light into this aperture. But what about the diameter of the aperture? Is that doubling too? No, it turns out in order to double the area of the aperture, we need to multiply the diameter of the aperture by the square root of 2. This will end up doubling the area of the aperture. So then if we want to go up to the next aperture size, we're going to double the area again, because this is going to let in, again, double the amount of light as the previous aperture size. So again, in order to double the area, we're going to need to take the diameter size and multiply it by the square root of 2. And now we're going to have a diameter of 40 millimeters. So this number, the square root of 2, this is an important number because every time we multiply the diameter by the square root of 2, we're doubling the amount of light. Just the same if we're to do the opposite and divide the diameter by the square root of 2, we're going to get half the amount of light. So remember what I mentioned before, that the f-stop scale is a way to talk about the amount of light coming in with regard to the size of the aperture. So why don't we just make a scale of aperture sizes and say, oh, well, if you want to let in, a certain amount of light, just open up your aperture to 40 millimeters. Well, the reason is that not all lenses are the same, and this same aperture size is going to let in different amounts of light depending on the lens you use. I'll show you why. So here we have two different setups with two different amounts of light we want to get. Here on the top, we're getting a lot of light, and here on the bottom, we're getting not so much light. In the top here, in order to get this amount of light, we would need an aperture size of, say, 20 millimeters. And here on the bottom, in order to get this amount of light, we would need an aperture size of, say, 10 millimeters. In both of these examples, the lens is the same distance from the film. This distance is called the focal length, and in this example, the focal length is 40 millimeters. Okay, that's fine, but what if we have a lens way out here, say at a focal length of 80 millimeters? Well, now, in the top example, we're going to need an aperture size of, say, 40 millimeters in order to let in this same amount of light. And in the bottom example, we're going to now need an aperture size of, say, 20 millimeters in order to let in this amount of light. Do you see the problem yet? The size of the aperture is not the only thing determining how much light is coming in. For example, here's two same size apertures letting in different amounts of light. And here's two different size apertures letting in the same amount of light. So in order to really think about the amount of light coming in, we also need to think about the focal length as well as the size of the aperture. So if we're going to talk about the amount of light coming in by considering both the diameter and the focal length, let's look at how those would relate. So in the top example here, when we had our 40 millimeter focal length and our 20 millimeter aperture, that was letting in the same amount of light as when we had our 80 millimeter focal length and our 40 millimeter aperture. These are letting in the same amount of light. Just as down here on the bottom example, when we had a 40 millimeter focal length and a 10 millimeter aperture, that was letting in the same amount of light as an 80 millimeter focal length with a 20 millimeter aperture. Calculating these down, we see that in the top example, these are both equal to 2, and in the bottom example, these are both equal to 4. These don't mean anything in terms of units, like millimeters or units of light or anything like that. All they really represent is the proportion of focal length and aperture diameter that will let in a certain amount of light. That's it. That's all it represents. But this is so important because it means that no matter what lens setup you're using, if the focal length and the diameter come out to this proportion, then you're going to be letting in this amount of light. And this number here, that's the number used for the f-stop scale. This is why you can see you can have different sized lenses and know that despite being different size or shape, as long as you set it to the same f-stop number, you'll be getting the same amount of light. So here we have these three numbers here. We have the focal length, we have the diameter, and we have, x representing the proportion between these two, our f-stop number. How would we put these into a formula that we can use to see how they're all related? So in this example here, we would have our focal length divided by diameter is going to equal our x number, our f-stop number. Well, remember, f-stop's all about being able to know how wide open to make the diameter, so we need a formula that will tell us the diameter. So let's rewrite this formula like this. F divided by x equals d. Now, if you remember your high school math, we can swap these two, and these equations will still mean the same thing. They'll still be balanced out with each other. So now we can say at this focal length, if we want this amount of light, we need a diameter of this size. And this side of the equation here might look a little bit familiar because the f-stop or f number you may often see written like this, f/x, or with an actual number, f/2, just as an example. So now we're mostly there. We know what the f-stop number is and what it represents, the amount of light coming in, but we haven't learned how the f-stop scale works and why it uses such specific numbers. In order to understand how the f-stop scale works, we need to go back to the scale of apertures we were working with before. So remember these aperture sizes we were dealing with. Also remember that these aperture sizes are very specific. They're specific because we multiplied or divided the diameter by the square root of 2, depending on whether we want to double the amount of light or half the amount of light. So let's put our f-stop formula here and see how these relate. So we have our focal length divided by our x number, or f-stop number, gives us a diameter. So remember, if we're multiplying or dividing the diameter every time we go up or down the f-stop scale, in order to keep this equation balanced, we're going to need to do the opposite to x in this equation. So for example, let's say we're going to double the amount of light. Well, in order to do that, we need to multiply the diameter by the square root of 2. Now, in order to keep this equation balanced, we're going to need to divide the f-stop number by the square root of 2. Let's plug in a real example and see how this would work. So with these apertures, let's say we're dealing with a focal length of 40 millimeters. So let's take our 20 millimeter aperture size here, for example, and see what the f-stop number would be for this. Well, if we have our 40 millimeter focal length here, and we're ending up with a 20 millimeter diameter, that means our f-stop number is obviously going to be 2. So let's put 2 here as our f-stop number. Now, we want to go to the next size aperture and get double the amount of light. So we're going to have to multiply our diameter by the square root of 2 to double the amount of light. Well, that means, remember, we're going to have to divide our f-stop number by the square root of 2 in order to keep this balanced. So now we have a new f-stop number of 1.4. Now you see, every time we go up a number in the f-stop scale, we're dividing our f-stop number by the square root of 2. And every time we go down the scale, we're multiplying our f-stop number by the square root of 2. So even though the f-stop numbers seem kind of random, they're really not. They're just being divided or multiplied by the square root of 2, depending on if you want double the light or half the light. So now let's take a look at the f-stop scale itself. So here's the f-stop scale, and every point on this scale represents double the amount of light compared to the f-stop number below it. And remember, as we multiply the size of the diameter and it gets bigger and bigger, we're dividing the f-stop number and it gets smaller and smaller. So the small f-stop numbers here at the top represent larger apertures, and the larger f-stop numbers here at the bottom represent smaller apertures. The scale still looks confusing though, and I can imagine it'd be hard to remember this sequence of numbers. So I'm going to show you a small trick here that will make this scale easy to remember. Let's start at 1 and look at every other number. We have 1, 2, 4, 8, 16, 32. Starting to notice the pattern, every time we skip a number, we're doubling the number. Well, let's start at 1.4. 1.4, 2.8, 5.6, and then rounding, when we double again, we get 11, and then 22, and then 44. See the same pattern. We're just doubling the number every time we skip a number. So as long as you remember these first two numbers, 1 and 1.4, if you only remember these two numbers, you can build out the entire rest of the scale quickly and easily in your head just by skip counting and doubling each time, starting with 1 and 1.4. It makes it a lot easier to remember. Some last bits of information about f-stop. If someone says they're going up a stop or down a stop, that just means they're either going to a larger aperture size or a smaller aperture size. Going up a stop means you're doubling the amount of light. Going down a stop means you're halving the amount of light. If someone says they have a fast lens or a slow lens, that's just referring to the size of the aperture on that lens that it can do. A fast lens can have a wide open aperture, which means you can let in a lot of light. A slow lens will only be able to have a much smaller aperture and let in a lot less light. This means that on a fast lens, your shutter speed can be fast because you're letting in a lot of light all at once. You don't need it open that long. Same with a slow lens, you have a slower shutter speed because you need your shutter open longer in order to let in the right amount of light. Shutter speed is its own topic, and I'm going to be covering that in a separate video because it's too big of a topic to cover here. Depth of field is a subject that f-stop plays a crucial role in. Depth of field talks about the area of your photo that's in focus. So for instance, if you have a photo where you need a nice blurry background, or you need a landscape photo where you need everything in focus, that's what depth of field covers. And f-stop, as I said, plays a key role. So if you want to understand how to control this, I suggest you watch this video. Then we have lens ratings. And in lens ratings, you'll often see the maximum aperture size listed. So for instance, you might have an 80mm lens with an f4 as its maximum aperture size. Or you might see something like a 55mm to 200mm lens where the focal length can vary between these two. But at this focal length, you might have an aperture size of 4, where at this focal length, you'd have an aperture size of 5.6. This is due to the construction of the lens, where it will only allow a certain maximum aperture size at differing focal lengths. Lastly, when we say we have an aperture size of 20mm, we don't mean that the physical iris inside the camera, where we have our lens and our film and the iris here, it doesn't mean that the iris has a physical opening of 20mm. It may be actually much, much smaller than that. What we're talking about is if you were to look at the front of your camera straight into the entrance of your lens, you would see the aperture size looking like it's 20mm. That's what's 20mm, and that's what you're actually calculating with your f-stop, not the physical size itself. I want to mention this because if you happen to actually see the iris in your lens, you would be quite surprised to find that it's much, much smaller, usually, than the aperture size that you're going to find with your f-stop rating. So that's the end of this video. I hope I've answered a lot of questions for you and help you understand what f-stop is, and also an easy way to remember the whole f-stop scale. If you have any more questions, feel free to leave them in the comments, and thank you for watching. In this video, we're going to be talking about a concept called ISO. In digital film and video, this refers to the sensitivity of the sensor that's receiving the light for your film or video. Now, as you know, we have a picture, a digital photo or frame from a digital video, and it's made up of millions and millions of individual dots called pixels. Now, each of these individual dots is sensed by a single sensor in the camera. All these together make up a big sensor that is in the back of the camera, and this is kind of like the film of the camera. But that sensor is actually just a whole array of really tiny sensors. And then what these do is these sense the color coming in for an individual dot, and it sends it over here to a corresponding dot in the photo. What we're going to do is we're going to focus on a single one of these sensors and see what happens with it. So let's take a look at one of these sensors. Now, this sensor sitting here, it's going to be receiving light. We have some red light hitting it and some green light and some blue light. Now, the sensor's job is to take all this incoming light and figure out what color should be recorded for a particular dot over here in the picture, a particular pixel. Now, the way it records this is it basically looks at how much red, green, and blue there is coming into the picture. So, first it's going to look at, okay, so how much red is coming in? And we're going to say, okay, maybe this much. And then it's going to take a look and see, okay, how much green is there coming in? Maybe this much. And finally, how much blue is coming in. Now these three colors together combine to make up a single color for this pixel, and that's what gets recorded. Now up top here, this would be considered, you know, the maximum amount of light it can sense. Say, we'll just mark it 100%. This is 100%. Now, what it's recording is how much red, how much green, and how much blue. And so, for instance, you know, in this case, you might have, you know, 85% red, 50% green, maybe 75% blue. Now, that's all fine. In a regular picture we're taking, we get different amounts of light. But now let's take a look at what happens when we have a picture where we don't have quite so much light. So here, we're going to take, you know, same sensor, but this time when the light comes in, we find there's only this much light, this much red. It's a much dimmer photo, not as much light available, only this much green, and maybe this much blue. So, as you can see, this graph looks relatively similar to this graph. It's just that it's a lot dimmer. There's not quite as much light coming in. Now, normally, with this being 100%, or the top of the graph here, that's going to show us a pretty dim pixel. But we can tell the camera, well, don't treat this as 100%. Let's pretend that this is 100%. So say, forget that, say that this is 100%, and let's treat these light levels accordingly. Now, this is getting scaled up to this. You see how that works? So now, this sensor could consider that it could brighten up the pixel by just treating the top of its sensing range as down here instead of thinking about it way up here. In a perfect world, that's all well and good because this sensor is just receiving the light and we just scale it up. No big deal. Well, we don't live in a perfect world, and these sensors are electronic, and with that there are some problems that come into play. And we're going to take a look at that. It's a little bit technical, but it's worth understanding why this happens. So let's say you have an electrical wire here, and in this electrical wire you have an electrical signal traveling along the wire. As this signal travels, it actually gives off a magnetic field around it. And this magnetic field is always there, unless we put some like shielding around the wire to prevent these from, flowing out. Well, what happens if we have another wire passing right by it, say right here? Well, it might have its own electrical signal traveling along this wire, and it's going to be giving out its own magnetic field. Well, when these two cross, these signals interfere with each other. This signal interferes with that one, and this one interferes with that one. As a result, this signal that's passing through the wire actually gets changed just a tiny amount. So how does that affect us here? Well, we have this whole sensor with all these little tiny sensors on it. Well, they're in a camera with lots of other electronic equipment. And as you can imagine, there are, wires passing behind it, around it, near it, You have just lots of stuff going on in this camera. It's on a whole circuit board and everything. Well, all of that electronic activity is actually interfering with these sensors, and it kind of changes the signal that it receives a bit. So if we take a look at what happens on a completely black room with no light coming in at all, let's say you have the lens cap on or something like that. So here you have the red, green, and blue. Because of this interference, it's actually going to make the sensor think it's sensing a little bit of red and a little bit of green and a little bit of blue. Just a tiny bit. Not a lot, but enough that the sensor actually thinks it's sensing something. And so it records it as just, a little bit of color variation for this particular dot. Now, what happens when you actually have light coming in? Well, this kind of gets layered on, this interference or this noise. And so the color that it's actually recording is just a tiny bit different than it actually is because of this interference happening, causing some noise in the recording of the color. That's usually not that big of a deal. If you have plenty of light coming in, this is just a teeny tiny amount, not a big deal. But what happens when you have not so much light coming in? Well, so we have this teeny tiny amount of interference, teeny tiny amount of noise, not as big of a deal. You can see it's kind of affecting the relative size of this because, this is a little bit and this is not so high. But what happens when we scale up? Well, this tiny little bit of noise all of a sudden becomes not so tiny because we're scaling everything up, including the interference. So what you end up with is when you're scaling up the signal, the noise also scales up too. So you end up getting more noise in your picture. Now, this is where the term ISO comes in, because people have determined ratings for how much noise there is in a picture or how much you're scaling it up actually. And the higher the number, like let's say we have an ISO number of 100, well, we're probably looking at something along the lines of this, where we're only going to see a tiny bit of noise and it's not scaled up at all. But then we go to something like 400. Well, now we're starting to scale things up, and so the noise starts getting a little bit more. And so then we go to 800 or 1,000. Now we're scaling up a lot. We might be scaling up, we might be treating this as the top range and saying this is 100%. Well, you can see how the noise is affected there. It's going to scale up way high. So think of it this way, as the higher your ISO, the more noise you're introducing into your picture because of this interference. Now, newer cameras have much better sensors that are able to not pick up all this electronic noise. So they can scale up much higher and not have this noise affect the final picture. Some of the newest cameras can scale like thousands of times up, and you still won't really have much noise in the picture, which is really nice when you're having to shoot in areas where there's really not much light. In some cameras, this will also be called the gain, and so you may see it referred to as gain instead of ISO, but it's really the same thing. It's just scaling up the signal to get a new signal, but in doing so, you're kind of bringing this noise along with it. I hope this helps. In this video, we're going to cover a concept called depth of field. You'll see this written as DOF. First, we're going to understand what depth of field actually means, and then we're going to look at how it works, and then we're going to look at how to control it. So the first thing, let's see what it means. So let's say we have our camera here, and we've got our lens, and we have this area that the camera can see. Now in that area we might have a tree here and maybe some apples, and what we're actually going to take a photograph of is the tree. That means that this area here that contains the tree, this distance from the camera to this distance of the camera is the area that we're interested. It's the area we want to be in focus. So this area is called the field. This is what we're taking a photograph of. What we're interested in is the depth of this field. So that's what we're looking at when we say depth of field, is the depth of the field. We want to know, how can we control it? Can we make this deeper, shallower? In other words, what if we wanted to make it a deeper depth of field, meaning we wanted to include the apples, or make it shallower, so maybe we only have part of the tree in focus and leave the rest of it out of focus. So let's take a look at what's happening here. We have our film or sensor, we have our lens, and we have our subject, which in this case is a tree, and this camera is focused on this tree. That means that light from the tree is going to hit the lens and get refocused back here onto the film. So that means that this point here on the tree is getting refocused perfectly back to this point on the film or sensor. It doesn't mean that this is the only point in focus on the tree. It just means that everything from this distance from the camera is in focus. Really, any point along this line, when we're focused here, any point along this line is going to get refocused perfectly back to here on the film. Now, we're just going to use one point here just for demonstration purposes, because it's easier to understand what's happening with one point than to try to do it with all of them. So this point here that we're focused on, as we get closer to it, it gets more and more in focus, and as we get farther away from it, it gets more and more out of focus. So looking at what's happening here, as the light rays are spreading apart, it's getting more and more out of focus. Our eyes are a little bit forgiving, and they can spread apart a certain amount before we consider it to be out of focus. So there's kind of a limit here on either side where we consider, okay, that's too out of focus, this is too out of focus. And, you know, it's a little bit exaggerated for this diagram, but, you know, that's just what we're doing here. So this area here, as the light spreads apart, it's getting more and more out of focus. And that distance here from, say, here back to here, this is our depth of field. It's the area where, okay, now it starts to be in focus, and then it starts to go out of focus again. And again, because it's for any point along this line, this is really, you know, this whole area in here is what becomes in focus. Now we want to know, how can we control that? Well, if we want a wider depth of field, we need to make sure that this light is not spreading out too fast. If we want a shallower depth of field, we want to make sure the light spreads out fast enough so that by this point it's now too spread out, or by this point it's now too spread out for us to consider it in focus. So let's take a look closer in here and see what's actually happening, and then we'll understand how we can control it. So taking a closer look at our area of focus, we have this area here around the point that we're going to be focusing on here. Now, as the light spreads out, we have a limit here where things are still considered in focus. This is our depth of field here. This is the area that's in focus. Now, bear with me here. If you consider that this area that's in focus, like toothpaste, if we were to squish these lines together, push them this way and this way, this way and this way, well, and then we end up with lines that look like this. Well, what happens to the toothpaste? It squeezes up the tube. Right? Now, this is the area that's in focus. And it makes sense because, you know, the light is not spreading out quite so fast. So it's not going to get out of focus quite so fast, which means that a wider area is going to stay in focus. Same thing if we pull these lines closer together and we end up with lines like this. Now the light is spreading apart really fast. The toothpaste squeezes back up the tube, and now we end up with a much shorter depth of field, or much shallower depth of field. Here we end up with a wide depth of field. So what we really are wanting to focus on is how can we control how fast that light is spreading apart from this point we're focusing on. If we can make it spread apart slower, then we can get a wider depth of field. If we make it spread apart quickly, we get a shallower depth of field. So let's take a look at that. There's three main ways we're going to have control over this. So in the interest of time here, I've gone ahead and pre-drawn some things. These are the different types of depths of field we're going for. Our normal standard depth of field, nice wide depth of field, and our shallow, smaller depth of field. And then our basic example setup we've been using to show how this works. Now what we want to look at is what we can do to control our depth of field and achieve either this depth of field or this depth of field. So in this first example, we're going to leave our subject where it is, and what we're going to do is we're going to move the camera much farther away from our subject. We're going to move away from it. And as you can see what this does with the light, this now causes the light to spread apart much more slowly, and we end up with the toothpaste squeezing down the tube here, and we end up with a very wide depth of field. Now again, remember that when we're using these examples here, we're not saying that this is the only area in focus. We're saying that this area from this point forward all the way back to this point, just because we're dealing with this point here, but it could be any of these points along the line. So this depth of field is really, you know, this whole area here. So as you can see, if we move the camera away from the subject, we're going to achieve a wider depth of field. Now in this example down here, we're going to move the camera very close to the subject, and we'll see what that does. We now end up with a very shallow depth of field because the light is spreading apart much more quickly, and we get our nice shallow depth of field. So again, if you want a wide depth of field, move away from your subject. If you want a shallow depth of field, move much closer to your subject. We're going to list this first method up here so we can keep track of these. And this is distance to subject. Okay, let's look at the next method here. So in this method, again, we're going to leave the subject where it is. Now, before we continue here, I want to explain something. This distance from the lens to the film is called focal length. Now I'm going to do a whole separate video about focal length because it's really its own subject that could have its own explanation, but you should know that that's what this is called. The distance from the film to the center of the lens is the focal length, and you'll see this measured in millimeters. So for instance, your lens might have a rating saying it's a 28 millimeter lens, or a 35 millimeter lens, or it could be a 300 millimeter lens, and what that's referring to is this distance. And we're going to use a change in the focal length to adjust our depth of field. So let's see how that works. So we're going to leave the film where it is. For both of these examples, we're going to leave the film in the same place and leave our subject in the same place. So we're not actually moving any closer to our subject or farther away. What we are going to do is we're going to adjust the focal length. So if we want a wide depth of field, we want to have our lens closer to our film so that we end up with a nice wide depth of field. So as you can see, we'll have a nice wide depth of field here. Toothpaste squeezes down the tube as these get tighter together, and we end up with our wide depth of field. Now we're going to move the lens a lot farther from the film, and as you can see, that's now going to achieve a nice shallow depth of field because the light is going to be spreading apart much more quickly than before with a nice short focal length. So here's our focal length is nice and long to achieve a shallow depth of field, and nice and short to achieve a wide depth of field. Now again, this is a very exaggerated example of what's going on just so you can see, but this is actually what's happening. So let's list that over here up in our second way we can adjust our depth of field here, which is focal length. Okay, so let's take a look at the third method of adjusting our depth of field. For this example, we're going to leave the subject where it is, and we're going to leave the film where it is, and we're going to leave the lens where it is. Okay, so if we're leaving all that the same, what is there to change? Well, this is talking about a subject that we haven't covered yet, which is something called the iris. The iris is a mechanism inside the camera that opens and closes a hole to let light through from the lens to hit the back of the camera. And so you might have this mechanism in here with a hole that can get bigger or smaller. The hole itself is called the aperture. The mechanism that creates that hole is called the iris. So here we have the iris at this size, and it lets the light through, and we get our depth of field. Now what happens if we have our iris here, but instead of a nice big hole, now we're just going to open it up just a little bit. We're only going to open up this little hole here and let some light through. Well, what happens? Well, our light can only go so far in terms of spreading out. And as you can see, what we end up with is this nice wide depth of field. Does that make sense? So by closing down this aperture, we end up with a wider depth of field. When we open it back up, we end up with a shallower depth of field. Now the size of the aperture is often referred to as an f-stop. And you'll often see this on your lens as either f-stop or f-number or on the display on your camera. And this is referring to the size of that hole. The way the rating scale for an f-stop actually works in reverse to the size of the hole, meaning that if you have an f-stop of 1.4, for instance, you're looking at a very wide open aperture. Then you go up the f-stop scale to say 2.8, and now it's closed down a little bit more, then 5.6, then 11. These are examples of f-stop numbers you may see. The higher up the f-stop scale you go, the smaller the aperture. And this is important because you can think of it as the higher the f-stop, the wider your depth of field. because if we go all the way up to 11 here, we're getting a nice closed down iris with a small aperture, so we get a nice wide depth of field. So thinking of it this way, we have a large aperture to a small aperture, okay, and then we have a small depth of field to a wide depth of field. Okay? So let's mark this down as our third method here for adjusting depth of field, which is the aperture, or f-stop. So we have our subject distance, we have focal length, and we have aperture, or f-stop. So if we want to look at what these do, if we want a nice wide depth of field, we want our subject far. If we want a shallow depth of field, we want our subject close. If we want a wide depth of field, we want a short focal length. For a shallow depth of field, we want a long focal length. So for aperture, if we want a wide depth of field, we want a small aperture, which of course means a large f-stop. And if we want a shallow depth of field, we want a large aperture, which of course means a small f-stop. So I hope this video has given you a good overview of depth of field and what it means and how it works. If you have any questions, feel free to leave it in a comment and I will answer it as best as I can. We glossed over a lot of things here. There's lots of details and exceptions and so on and so forth about how this all works, and those are subjects for later videos, but I hope this has helped give you a good understanding.